So we're in a, we're indoors, which is really cool. Today's gonna be a little different.
Yeah, it's not actually circular.
Okay.
It's never actually circular.
How much would something like this cost? Like if a surgeon wanted to
Hit it freakishly hard.
Really?
Yeah. This is our a GPS system. So this is...
Did you say GPS? Today we're with Corey. Thank you so much for meeting up with me.
Of course.
Okay. Corey has invited me out. Last week, had the pleasure of meeting your dad. So he's their lead at his shop, fixing airplanes all day. So Corey, what do you do? I guess like what do we like?
Yeah,
because I can't even explain it.
I am an industrial designer for a company called Exactech, and we make orthopedic implants and instruments.
So you've actually like designed these tools that we'll look at today. The trays that they're in, are these what like the surgeon would have these actual trays in their operating?
Yes.
Really?
Yeah.
Okay.
So this would be, these are called instrument sets. So the surgeon would be doing the surgery, and then he would be turning around, and we would have OR or scrub techs that would be handing the surgeon the instrumentation or getting the instrumentation ready for him to do the surgery. This is to rebuild the bone that is resected or cut out of the patient so that they have full mobility of their arm. So these are kind of specialty instruments. We call them reamers. The area that we're in right now, we call it our sawbones lab. So these are fake mock-up bones of a humerus. And so these are different instrumentation to go down the IM of the bone and to actually cut and more or less drill this specific diameter. This is basically reaming out a cylindrical portion inside of the bone to accept another implant. So if we're able to ream...
So this is something the surgeon would be doing?
Yes, so the surgeon would be doing this. We also have indication marks on all the reamers to tell them like not to go too deep.
Yeah. So everybody has like can I touch this thing?
Yeah, of course.
Everybody has like that?
Yeah.
Already? And
Yeah, it's not actually circular.
Okay.
It's never actually circular.
Okay, that makes sense.
Sometimes they are kind of circular, but sometimes they could just be crazy shapes.
Gotcha.
And most of the time, they're not actually perfectly aligned with the outside of the bone. Sometimes the position of the IM can be way off.
Okay.
And so this essentially just prepares the bone to be perfect. I was tasked to make something that would be rotationally stable with the bone. So we have these things that we call collars.
Okay.
So these collars go over the outside of the humerus, and we have them in different sizes. All of what you're seeing here is called trials. So we're trialing the implants in the position before we would, so to speak, what we call buy it. So before you're opening the implants, which are sterile packed, and before they peel them, and once they've peeled and opened the implants, they've bought them.
Oh, so this is like you're measuring which one you need.
Correct.
I see.
So we're just making sure that what they are using and before they actually open the implants and buy them.
You're not like opening like 3 or 4.
Yeah, exactly. And then this goes down actually into the IM, and then this would be, you can also do dual eccentricity, so you can offset it, because like I was saying, the center of that is not always actually in the center of the bone.
Ah, I see.
So we need to compensate and have different offsets built in so that we're able to have it actually fit. They usually use a specific type of saw to cut the resection. And
so these tools would also be in the operating room?
Yes, these would. Okay. So these are general OR tools, a really fancy drill, and then like a reciprocating saw. Okay. Just really fancy versions of them. Not a Milwaukee kind of thing. And then, so if they do cut that though, it might not necessarily be perpendicular to what they actually just cut. So we have planers.
Oh, that looks crazy.
Yeah, so it's essentially this goes on the thing, and then of course I grabbed the wrong size. Essentially they put this on a drill, and then this gets this perpendicular to what you just reamed.
Okay.
If the surgeon resected this much bone, we need to build that back at the proper height. The way our muscles work are very specific on the lengths. So we are trying to achieve exactly what they took out. We want to achieve the same thing, and we want to build that back up. We have different middle segments. So these are, we call them middle segments here. They're essentially kind of like a Lego building block, like I was saying. And so we use just standard hexes all the time. So now we're basically trying to rebuild what we just cut away. So then these pieces are called our proximal bodies, a smaller tuberosity all the way up to a very large tuberosity.
Okay.
This is kind of what we determine when we do the cadaveric studies, is to make sure that the sizing of things like this aren't way too big or way too small, and that they'll fit a majority of the population.
Oh, I see.
That goes on there. I made this little locking ring that essentially slides over and keeps the rotation, so now it doesn't spin. So there's different ways that we do procedures. So some of them we do a reverse. So naturally, our bone is kind of like a ball and socket. You have cartilage in between there, and then these ride when you're picking your arm up. Your shoulder blade actually moves as well, just a little bit, but your humerus is articulating on the surface. So this is the head, your humeral head. This is how we were made, and this is how it works now.
Okay.
But over the years, we have found that there's different ways to do it. And instead of having the ball and socket on this side, we flip it. So we will put, we'll put what we call a base plate. So this will go into the glenoid side, which then puts the ball on this side.
Oh, that's genius.
Yeah.
I like, that's literally like a genius.
It just flips it.
It's making this, that's so crazy.
And then instead of, so we took the glenoid and then we put it on this side, and now this articulates on this side. There's several reasons we do this. One is for stability.
Okay.
So a lot of patients that are receiving implants are older, their joint is not very stable. And sometimes they'll have so much wear on their bone that this is basically gone. So that's a pretty standard procedure, is a reverse. Once he gets to this point, then the surgeon is able to put a tray in there, which we have these. These are all still trials, tooling.
And so you build these tools as well?
Yeah, so
everything.
Yeah, so these hex drivers, so something as simple as this hex driver, I designed that. We even have
what is that?
Specialty crazy hammers that
That's a hammer.
Yeah, and we call it the dog whisperer because when you hit it with something, it's like a tuning fork.
Really?
Yeah, so it echoes really loud. This is technically a general OR instrument, but it has a slot because when they're impacting versus when something is in the bone and they need to get it out, they do what we call retrograde impaction. So they hit on something to rip it out.
Oh, so that's what
it's kind of, yeah.
Okay.
So like, I'm not saying that this is something that they necessarily do, but let's say that they ream and this is really tight in the joint, they can then
I see.
rip it out.
Gotcha.
They don't actually use this for what I just showed, but that's essentially what it's for.
Okay.
So then they can build up to the tray, and then we have different pieces of plastic as well that they can snap into here. And this is all like a quick snaps, because sometimes they'll change this out rapidly to figure out sizing, because we have different sizes of the plastic as well. Sometimes the resection, instead of being here, can be way down here. Oh. So somebody may have bone cancer that is 70% of their humerus, so they're taking out 70%. So then we have different and taller segments, so you can build up a massive.
Oh, they like snap together?
Yeah.
Oh, okay.
Yeah. So you can actually build up and.
Oh.
So they snap together, and then they have a locking ring for rotation, and so you can keep snapping and basically build as much as you want all the way up. So when they take all this apart and they decide that this is the sizing they want to go with, we have the implant, which has a special type of coating inside here. It's actually titanium that they put with plasma, and they shoot plasma titanium out of a gun onto this titanium.
What?
And it sticks to it.
Okay.
And so And bone grows to really either porous things like a sponge, it grows to really porous structures, or it grows to really abrasive structures. It doesn't like to, it won't really grow to smooth things. I designed to have these fins be, they are able to flex.
Really?
So they'll take this and they actually will hammer this down over the outside of the bone in order to have it press fit on the outside of this bone. And we also do some crazy things with 3D printing implants as well.
Really?
Yeah, so we have, this is a totally different product line. This actually goes onto the glenoid, so this would be an anatomic. So this goes inside the glenoid here, and this piece is a new product that we came out with a couple years ago.
That's crazy.
So these pegs are actually 3D printed out of titanium, and they have,
What?
yeah. And I came up with, me and another friend I work with came up with an idea of like, inside of these, there is a special material, and then we actually bond this plastic to the titanium.
Wow.
Yeah, so this is, we print the pegs, and then we mold the plastic to the actual pegs.
Wow. So that's not going anywhere.
No, it's super strong product. It essentially, this is more or less replacing your cartilage. So
So I have a question.
yeah.
I mean, these tools look so great. Like automotive, you get a fancier wrench or a fancier Milwaukee impact.
Yeah.
Like they know how to use it. How does the surgeon know how to use these tools? Because I'm assuming when they get a new product line or something like that, it would be completely different.
We'll bring in reps, or we'll bring in, and a rep is a person that Exactech, essentially, we have a contract with them that they are kind of like a salesperson, and they will sell the implants and walk the surgeon through the procedure to make sure that there's no hiccups and that they're using them correctly and not skipping steps and things of that nature. But we'll have big training, more or less. So we'll either fly to the surgeon, or we'll bring the surgeon to some location that we deem, and we'll have a big, if the surgeon wants to do a cadaver, we'll do a cadaver lab with them. And we'll physically walk them through this, or we'll give the surgeon an overview of how to use everything, because we have special things that are called optics. So it's like it's exactly what I'm showing you, but on a pamphlet, a big long book of exactly how to do it. And we make special renderings, so fancy pictures to show them exactly how to do the procedure with the instruments.
So it's kind of up to the surgeon if he wants.
Yeah.
I see. How much would something like this cost? Like if a surgeon wanted to...
So if a surgeon decides to go with this product, then we actually ship these to him for free.
Completely free?
Or to the surgeon. They're obviously female surgeons. So, and very good ones.
Sure.
So we would ship the entire instrument for free to them. We sell the implants, and the instruments come for free.
That makes way more sense. Okay.
Yeah. These entire kits, they take them and put them in an autoclave. That's why they have holes in all the sides, and everything has to be able to be washed by the cleaning staff, and they basically put like parts washers. They put them in a parts washer. That's the thing I love about medical is every single instrument we have is one-off. There's basically no other. Sometimes we use something simple like a really fancy screwdriver handle or a T-handle. We try and come up with one design and make sure that will work through every product line, so we're not constantly making brand new screwdriver and T-handles. But for the most part, every single instrument in here is designed for one specific task, and that's all it ever does. So something like this is a slap hammer. So this is a crazy slap hammer. Yeah. So you this basically. So this is still a trial, but if this was an implant in the bone, which I was lacking in saying, once they smash this collar over the outside, they actually use a special type of cement, which is it's kind of like an epoxy that they put down the IM, and they push this down in, and that cements the inside to here. So if they need to revise this, they would thread this huge slap hammer on there. And because that's cemented in here and maybe it has grown in a little bit, then they can slap hammer and rip that thing out without having to cut this entire bone to pieces in order to get this out. This is basically an instrument so that when they're putting, this clicks onto this big handle, which this is just a really fancy push button handle, put the implant onto the construct. And because we use, in orthopedics, we use a lot of tapers. Okay. So a lot of this is Morris taper. So this is something to where they can now do that and use our hammer and hammer it together.
Oh, wow. Okay.
Yeah. And so this physically bonds the two. This is basically an impactor piece, but it also works with threading separate rods in there. And these are called retroversion rods. So this rod is essentially to make sure that we can have the implant align with the forearm. The instrumentation side, this is a pretty basic kit. There's nothing too crazy here.
Really? Like this looks just insane.
Yeah, this is a pretty simple one. I mean, super simple stuff like this is basically like a pickle fork.
Okay.
So it clicks on the same handle, and this would be if you have two pieces that are taper locked together, you can put this in between it, and this separates the tapers, just like a pickle fork in automotive.
Huh. So how do you go about? I'm sure there's a big process, but how do you design this stuff? Like, is it like you start with paper, or you just draw out a sketch or something?
The very beginnings of the process, I'll sketch it. I'll model it, and then we'll go to a cadaver lab. Okay. And myself and the engineer on the project, we will work with our design team surgeons, and most of the time, the first, second, sometimes third cadaver lab are just basically everything you see here, but printed out of plastic. Okay. So we have many plastic 3D printers, many of them. We use a CAD software that's called NX.
Kind of like SolidWorks, or?
Yeah, it's basically like SolidWorks. All the big engineering companies. I know Ford and I'm pretty sure Chevy both use NX for doing motor building and development, and with even the shape of the car or truck.
Really?
I know Boeing also uses it, and I believe Caterpillar as well uses NX.
Huh. Yeah, looks like you have a bunch of other tools here. What?
Yeah, so this is a totally different approach. This is, so if you hear somebody's like, oh, I just got a total shoulder replacement, these are the tools that we have made to put a shoulder replacement in.
And you designed these as well?
I designed a pretty good amount of them. This was a larger project. So this instrument kit is our bread and butter. This is how we put in what I was talking about, a primary and a reverse. So these are the main tools that surgeons are using every single day all across the US and the world to put in the implants. This whole kit basically puts this implant in.
Oh, okay.
And then we have certain instruments, like this is a funny instrument I made that's called, we call it the dolphin, because it kind of looks like a dolphin. So the implant actually has a special shape, so they can click and it auto locks.
Oh, wow.
So then, because it's in a really tight space, so in the backside of the implant has to line up. So this is an instrument that they're able to hold on to, and the scrub tech would click this on and then hand the surgeon the instrument with the implant, and then he's able to use it as leveraged and get it in because it's a very tight space inside. We also have other multiple instruments to do the same thing. So we have essentially like a universal impactor handle that then has a taper on it, and they can hit this very lightly on the back table. So now if they need to get around, there's other instrumentation that will always be inside the joint. So we have things like retractors, which these are basically like big pry bars to hold the muscles out of the way. Oh, wow. And we have tons of different types of tips on them. So different tips work for different things, and they use them in different scenarios.
Are these like the same thing as the planer?
Yeah. So this is these are called reamers. So these are glenoid reamers. The surgeon will have this attached to a drill,
Okay.
and essentially he will be holding it like this. It clicks onto these reamers, and now we have a pilot tip.
Okay.
Because something like this will walk all over the bone. So they'll put a very small hole in the center of the glenoid.
Okay.
And then they're able to put this in and ream the surface to this exact curvature we've made this curvature exactly a specific size in order to match up with the bottom of the implant. So the implant fits perfectly onto the bone.
That's wild. And what are all these plastic pieces?
So all the plastic is to rebuild what the implant would be replicating. So this would be going into a different implant, and these all have an articular surface so that this unit, which is called a glenosphere, is able to ride on this. Even more specialty tools, and this is a gear multiplier. So as you put in 1 torque in here and you spin this, it outputs a much greater torque and is able to break a special screw that we have that is designed to break.
Okay.
What we used to have to do is have a big T handle on. We used to have this instrument right here that would go onto this screw, which this is the screw. So the head of the screw actually snaps right at the junction right there.
Oh, so just like an automotive.
Yeah, it's like a torque to yield is exactly what this is. So this holds a special part of the implant together, and they used to have to hold with a special fork back in the day with one hand and then spin this T handle and snap this. And it is not the easiest thing in the world to do. So I was tasked with trying to come up with a better way to break that a little easier. So we have specialty tips that are able to click onto a handle, and this is essentially a counter torque. So you can't break something with a multiplier unless you have an opposite force. So if I put this on the screw and I spin it, it just spins the entire outside body.
Oh, okay.
So this goes into the implant. So the screw goes through this tray, and it goes into the stem. So this stem is actually what goes into the bone. And then this piece goes into this tray, and that is your counter torque. So this isn't able to spin.
I see.
And then this whole giant construct goes through there, and then once it's locked in, now I'm on the head of the screw, and you essentially turn this.
Gotcha.
Very little pressure is applied here, which outputs a very large pressure here and breaks it. A lot of things we try and use are, like I was saying, are just as fast as they possibly can to hand it to the surgeon. The less time under anesthesia and with an open wound, the better. This is another really fun specialty. This is called a broach handle. So these are...
what is that?
Yeah, so these are broaches. So this goes inside of the actual bone, and this cuts out. So these are incredibly sharp teeth, and these are like a reamer, kind of. But they are cutting this exact shape inside the bone. So we have a broach handle that it snaps onto it, and they take the hammer and they wail on this and hit it freakishly hard.
Really?
Yeah. Because they're sinking this incrementally down into the bone. Yeah, so the size that we just reamed was a 7. So this diameter on this is also a 7. But obviously this doesn't fit. So this is where we would then use the broach.
Oh, I'm excited to see this.
So then we put the broach on, and hopefully this holds the bone. You can hear the tuning fork.
Yeah.
So, and then this is why I was saying sometimes they can pop it back out because it gets stuck.
I see.
So this is... So once they put the broach in there,
Okay.
then depending, like this one, you know, particularly is a little too big or a little too small, so they'll take that out, and then they go up to the next size. So then they're able to then keep broaching. And then we're trying to get it flush with the cut. So we're able to take that out. And now they can trial everything off of the actual broach, because that stays in the bone just for trialing purposes.
I see, okay.
So we have specific shapes on everything to keep it from moving and rotating. So then they can put that in there, and then they can put the liner trial on, which is a snap click. And then they can do a range of motion. Obviously, this is not the proper fit.
Yeah.
It should be way bigger, but this is just a general idea of kind of what, you know, how these are function. Yeah.
So wait, so when this comes out, what goes in its place?
Yeah, so when that comes out, so then they would put this back on. And something I failed to mention was, so we actually have special shafts that depending on if this is a right or left shoulder, they thread this in, and we have markings on the actual broach itself that determines what's called retroversion. So this is more or less to make sure if they put it in 30 degrees retroversion, that they want to make sure when they're cutting the shape, that they're not cutting the shape in like this.
Oh, I see.
Or cutting the shape in like this, that they're actually cutting it in the orientation that they're supposed to be.
Okay.
Because it is possible to do that, even though you shouldn't be, but it is possible to do that. So once you're able to take that out, then we have other instrumentation to put in. So this would be the stem that is an actual implant, and this is a stem inserter that then they can put that in, and they will implant it, and that gets press fit. So that stem is press fit into the actual bone.
Does that have like the titanium?
It has not entirely the same thing, but it has what we call a grit blast. But yes, the bone, the inside, this pink that's represented here is called cancellous bone, which is our spongy bone. And then the outside is called our cortical. So our cortical is like a shell, and it's much harder bone than the inside. The inside is sometimes mush, like actual mush.
No way.
Yeah, it's very soft. But the cancellous will physically grow to this stem.
Okay.
So then once they get that put in place, then they can rebuild exactly what they just trialed. So they can then put the screw in, and once they put the screw in, they would then be able to, they'd have to break the head of the screw off. We have things put in place to where they can't finish putting this on unless this is broken off. So we even think downstream to make sure that, because you always want to break the screw off in there.
Sure.
But if they don't, you can't physically put this implant, the next step. You can't go to the next step unless you fully finish the first step. And then we have impactor tips. So we have an impactor tip, and then you hit this, and that physically locks this to this. And it uses a special type of mechanism to lock them together. When I was talking earlier about being able to drill for the center cage for an implant like this, if you just take a regular drill, like we all have, and you put it on a piece of wood, it just goes everywhere. So we have instruments that hold on. Basically, we call them drill guides.
Okay.
So you would be able to, the surgeon can hold it like this, and then when he has his drill bit clicked on to his drill, then he's able to put the drill bit, or the surgeon is able to put the drill bit through here and drill. So then he is controlling this, and this is a full depth stop, so he can't over drill. Can't go too deep. We don't really like surgeons to take an implant out of this very special packaging we have, and with his hands or her hands, and physically put it in. We want them to have instruments to do that. We also even have specialty instruments that grab and have springs that lock and hold it on, and then they're able to then hold it and then put it inside the implant and impact on the back of that so that they don't drop it. Because if you drop this on the ground in the OR, this is now trash.
Oh, really?
Yeah, and they have to buy another one.
Oh, no.
So a lot of really fun cutters. So if we go back to this step here, slightly jumping all over the place, but I'm trying not to.
It's totally fine.
Put this brooch back in. So we have the brooch in there, then we have different things that we call them calcar planers.
Okay.
So these are special blades that click onto another special post. So they basically click and spin. And now we can take this, and let's say that the surgeon put the brooch in, and this face where when he cut it, because he's using a blade that a big saw, that he could have the orientation of the blade off.
Oh, right, okay.
And a little bit goes a long way. So if it's really far off, they can put a post inside the brooch, and then this goes into our drill. And then they're able to then put this, and this guides this.
Oh.
And then it spins and it reams this surface at a perfect angle that we want, but it's parallel to the face of the brooch.
Oh, that makes perfect sense.
Yeah, so it's a cleanup. This is a cleanup stage. Some surgeons do freehand cut this. So this is the anatomic cut, but some surgeons might be better at that than others. We actually even offer guides that are able to go off of the reamer. So if we had a reamer down in there,
okay,
and we're able to have a guide that clamps on the outside, and that keeps this orientation. Basically, these are now parallel with each other, these two axes.
Oh, yeah, I see. Okay.
And we have different cut guides that then click into this, and now, and you can adjust the height of this, and then the saw blade then runs. And this also moves.
Yeah.
And then you're able to then and pen this to the bone, and then your saw blade runs in between a guide and cuts that perfect.
Oh, that's genius.
Yeah, so then they can't mess it up, more or less. Ergonomics is a very difficult thing to please everybody, but we try and be really good about ergonomics to make sure that things feel good in the hands, and that that's something like all the big tool companies, they're always making sure that handles feel well, or there's no weird pinch points on certain instrumentation, or if you need to thread a certain thing in, that by color coding that this is a touch point. So you would know that this is supposed to be threaded into, where did I put that stem? Oh, so this would be threaded into the stem, and you would know that this threads in there. So this is actually an instrument to rip this stem out.
So how long ago did this stuff come out? Is this relatively new?
This is a decently new product. I'm going to say the wrong thing, and an engineer's going to yell at me. I think it was 2019.
Oh, okay, so fairly new.
Or no, that's wrong. I think it was 2017.
Okay.
I think it was 2017.
Okay. But still, it seems fairly new.
Yeah, it's fairly new.
And so what is this over here? Is this part of yours as well?
Yeah, so this is I don't know the whole ins and outs, but this is our a GPS system. So this is...
Did you say GPS?
Yeah, that's what we call it, Exactech GPS.
Really?
So basically we, this is knee, but we have a system that is able to use a computer screen.
Okay.
And the computer screen is connected to what we call trackers. And the trackers are attached to the bone before they do any cutting or reaming. And the tracker is always turned on, and it's basically reading. And then they're able to use a special tool, and they can paint this surface is what we call it, and this sends an audible click to this system and will map what the patient's physical bone is, and we'll put it into a software and we'll show the bone on the software, and then it will help the surgeon cut and drill and ream to what they planned to do on the computer.
No way, that's crazy.
Yeah, and it's very, very, very accurate in degrees, and it's very, very accurate in depth if you're drilling.
Gotcha.
Or if you're drilling so you don't drill off axis.
That's just crazy.
Yeah, it takes the guesswork out of, because before they take a CT scan of the shoulder or the knee, and they then can do a mock surgery in the software and plan it. And they save that surgery. And then when they go and do the real surgery, then they replicate exactly what they did in the software, and the software is telling them how to do it.
Wow. That's amazing.
Yeah. And then we just have tons of different instrumentation in order to achieve that. So these are specific, like we have specific cut guides that are able to control the angulation of the blade that you can tilt. And all of the instruments that do this have to have a specific tracker on them to send feedback to the computer. So like I said, this is obviously knee, but we have specific instruments. So we have this reamer. I made this reamer driver. We have one as well that has a post, and the tracker sits back here and is able to communicate. So when they're drilling, they're not drilling off axis, or they don't go too deep. And this physically tells them on the screen when to stop.
That's amazing.
Yeah, it's
it's
a really cool technology. You can do, so right now, this entire kit that I showed you, we can do this entire system with GPS.
Really?
Yeah.
Gosh.
So it's all the way to the point to where if the surgeon does his mock surgery, his pre-planning, and says, I want to use a 38 millimeter, then the software tells them this is a 30, you plan for a 38. So when he clicks next on the screen, it says grab a 38.
Wow. This is just a whole nother world. I didn't really think about like a surgeon having a setup like this. I always imagine, a drill and maybe a saw, but I've never really thought about them having like a whole setup like this.
Yeah, it's definitely like I was saying, a one-off niche market that there's specific instruments for every little step.
Man.
And for every single product line, we have an entire system to do it. So this is actually even another little product line that we have. We have cool little acronyms for all of our products. We call this HAT.
Okay.
So this is humeral augmented tray. So this was another patent that we got on the implants to rebuild the humerus if somebody had an issue where they fell and their humerus shattered, and the surgeon is not able to do a fracture case, which is basically taking all the bone pieces and pulling them back together, and this fixes that. So if they're not able to redo that, we have different instruments that I took this idea that we've had for a long time and turned it into this. So these are basically acting exactly the same. This is just filling the cavity that you have lost. So if you had a bone on your tuberosities that these broke off, or they sometimes in fractures, if these break off, they actually absorb. So like your body absorbs the actual pieces.
Okay.
Or if they get infected and the surgeon needs to remove it, or for multiple reasons, this piece will go in and will rebuild on this outer portion, and it will rebuild what you are missing. So then your muscles can slide over and work the way that they naturally work.
Sure.
Even if we want to get more complex with biomechanics, meaning like if you had a small tuberosity and your deltoid is barely pushing on this, and your deltoid is what helps pick up your arm, but maybe the surgeon wants to put something on that has a bigger tuberosity, which actually causes your deltoid to stretch more, which actually gives you more mechanical advantage
Really?
for your arm
Huh.
to work properly. The biomechanics, we really at Exactech, we really have tried to teach biomechanics and to be the best, I think, in market with it. And we have some incredibly smart people who know way more about that than I do.
That's amazing.
Yeah.
Everything you showed me is just, I've never seen anything like this before. So, okay, this is going to be a little bit different because I always like to ask guys that have been doing this type of work for a long time if they have any advice for somebody that's interested. This is such a niche, I guess, industry. But I mean, if somebody wanted to, design tools or, design instruments or anything like that for a living, what would your advice be to somebody that's asking that?
I work with a lot of mechanical engineers and biomedical engineers. Maybe a design degree is a good way to go.
Yeah.
I don't know if you can actually get into this industry without an actual engineering or design degree. I'm not really sure.
What was it that you majored in?
Industrial design.
Industrial design. I see. Okay.
It's an engineering and kind of like an arts degree together, more or less.
Yeah.
So, but yeah.
That's amazing. Well, Corey, thank you again so much for taking the time out of your day. Like, this is just next world stuff. I can't believe it. It's so cool. I hope you guys enjoyed it as much as I did, because that's just not stuff I get to see every day. So, but if you have a setup you'd like to feature on this channel, you can hit me up on Instagram or just send me an email. But till the next one, we'll see you.
They give me a ton of freedom, and I work really closely with surgeons and work really closely with engineers, and we try and make the best product we possibly can for the patients.